Hello and welcome to the first tutorial of our new SimScale tutorial series. My name is Joseph and I'm your instructor for this tutorial where we have a look at fluid flow through a centrifugal pump. So first of all, the agenda for today. So I'm first going to cover what we are going to learn in this tutorial. Then we'll go through the steps involved in the simulation process. And at the end, there will be the step-by-step demo. If you want to skip over the intro, there are timestamps in the description. So if you want to jump straight into the demo, feel free to jump ahead. So what are you going to learn? Today you are going to learn how to set up and run an incompressible simulation, and we will make use of the so-called rotating zone. I will show you how you can assign topological entity sets inside of SimScale, what these are and why they are useful. We will assign boundary conditions, material and other properties to our simulation. That's what we call the processing step. We will also mesh the geometry with the SimScale standard meshing algorithm. Here you can see a big hexahedral element consisting of 8 smaller volumes. Please note that one volume consists of 8 vertices, 12 edges, and 6 faces. So the underlying equation to solve fluid flow problems is the so-called Navier-Stokes equation. I'm just putting it here on this slide because I think it's a very beautiful equation, and in case you want to see what each component means, you can pause and ponder for a moment to have a look at it. It's basically nothing else than Newton's second law of motion. So steps involved in a simulation. This will be very short. So how CFD works on a deeper level is that we have a physical problem which we will transform into a mathematical model, what we call PDEs, which stands for partial differential equations. These equations describe nature. Step 1 is that we mesh our CAD. This is the so-called pre-processing step. Step 2 is where we define our analysis type. This counts as a processing step. In step 3, we specify our fluid properties as well as boundary conditions. In step 4, we select numerical schemes. That means we can adapt solvers in interpolation schemes, for example. Step 5 is of course post-processing the results. That means we're trying to make sense of what we actually calculated. For example, we will have a look at pressure loss, gain, vorticity, forces and so on. But it really depends on your simulation and the quantities that you are interested in. To break this down in a more picturesque way, so we have the real-world problem transformed into PDEs, then into algebraic equations which can be solved by the computer, which is basically nothing else than code which is written by the developer, and then this code generates data for us, which we then can process. The more simplistic approach is a 3-step process, so we have the pre-processing step, processing step, and the post-processing step. So errors in CFD, especially for this kind of simulation, which I want to talk about now, is let's have a look at this backward-facing step. So what you can see is after this step, you can see some kind of recirculation zone, which is indicated by this circle, as you can see. And a bad idea is to cut the outlet. That means we cannot really see this physical phenomena of this recirculation zone. So that's a bad idea. What we do instead is to keep the outlet extended as it is to actually cover this physical phenomena. This is indicated on this slide in a more simplistic way. What we have to do is to define a proper distance to the area of interest to actually make sure that our flow is fully developed and enters in that sense into our fluid flow area. So if you have any questions regarding the slides or the formula that have been on the slides, feel free to reach out to us via the forum, and the power users, the staff, and I will make sure to reach out to you and help you out. With that being said, let's jump straight into the demo and let's get started. So once you imported the project, you can see 2 geometries. This is the first one, which is already prepared for you, and the second geometry being the original geometries you can see right here. So this is actually not useful for us because this geometry is first not watertight, and it also lacks the extended inlet and outlet as we have discussed in the slides. So if you want to learn more on how to actually do this and actually to have a proper model for your simulation setup, make sure to check out the documentation page, and there are articles linked inside the documentation page for this tutorial, which I'll link down in the description, which actually explains how you can prepare your geometry inside of Onshape. With that being said, let us just create the simulation from scratch. So I choose this geometry right here and I click on Create Simulation. I already know that I want to have the incompressible module activated or selected, so I click on it and click Create Simulation. If you need any help for your simulation, you can simply click on Need Help, and it will ask you some questions about your simulation and will give you some modules which you can choose from, as you can see. Once you hover over them, it gives you some selections. But I actually know in this case that I want to have incompressible, so I simply click Create Simulation. As you can see, it generated a tree for us on the left-hand side, so I already created the simulation beforehand, which is already post-processed and so on for later purposes. And here's the new one. So what you can do is also to give it meaningful names. Let's say test run 2, for example, let's call it that way. Just as a hint, if you use names, make sure to give it useful names and meaningful names. So the geometry has already been selected. It's our centrifugal pump and not the original geometry. And as you can also see, there are some information about the geometry right below the geometry itself. As for the material, we want to choose water. So we go to the material library, choose water. If there's any material you want to use, but it's not in the list, don't worry. Simply choose one material, and then you can adapt the material parameters as well as the viscosity model, as you can see right here. More information on the viscosity models in the documentation. So I choose my volume where water is flowing through, looks perfect, and I assign it to it. Next, we start assigning the boundary conditions, but before that, let me just show you the topological entity sets. So these have been predefined, as you can see. These are basically sets that define specific sets from our geometry. So if I click on walls, these are only the walls. If I click on impeller, this is the impeller which has already been selected for us. And local element size refinement, which we later on for local refinement, has been selected right here. This makes things way easier than to always select, reselect, and so on. So let's jump to boundary conditions, and you can see indicated by this red circle, we have to do it, otherwise we cannot start the simulation. So let's start with the velocity inlet. The velocity inlet will be right here, so we click on this face, and it will be a flow rate boundary condition with a volumetric flow, which is 8.5 to the power of -3 meter cubed per second. I click enter again, and it has been assigned. You see, it's green, so we are good to go. A common combination is to have velocity inlet pressure outlet. So in that sense, we choose another boundary condition, which is pressure outlet. We choose this as our pressure outlet phase. We assign it a mean value to it, which is 0 Pascal in this case, and we are good to go. The next thing we are going to do is to select the walls. And this has already been predefined by me here, walls, and I can just add wall, click on my wall, and what I then do is to have no slip and wall functions activated. If you don't know what this means, don't worry, there are some documentation entries explaining that, and there will be a video from my side following in the future where I explain what this actually means. So we are good to go, and we can save this boundary condition. What we're doing next is to go to advanced concepts, and we want the impeller to rotate, but not the impeller itself, but actually the cylinder that encloses the impeller. We go to rotating zones, create an MRF rotating zone. AMI is for transient approaches, but we have a steady state approach. Here we are in the rotating zone now. What we now have to do is to enter in the right coordinates. This is the wrong axis for now. It is the one axis in X direction. So if we use the right hand rule, you can see it's rotating counterclockwise in this direction. So that's what the axis shows, and it's very easy and very intuitive. Of course, what's missing is the rotational velocity, which is 350 rad per second. And we choose our MRF rotating zone, which is already predefined. Awesome. We can save that. And what we then do is we skip the numerics. So we're good with the numerics, and I wouldn't actually tweak it unless it's really necessary, and jump straight to the simulation control. There we type in iterations, because this is not real time. This is more of an iteration in terms of interpretation. 600 seconds, a delta t of 1 second, and we write it out one time at the end, which is 600, and the maximum runtime looks fine. We leave it as automatic right here. Of course, because I have the Pro version, I can choose up to 96 cores, and we can activate foam initialization right here, potential foam initialization, which enhances stability for velocity-driven flows, what we have in this case. So I activate that, save it, and then I can add result controls, because I want to have a look at forces and moments. Then I go to surface data, area average, select this face, and I can do the same area average for the outlet face. And you will see what that actually means in terms of interpreting the run or the run progress. Next step would be to mesh our geometry. And for the meshing, I have already prepared a mesh, as you can see. And I have used the standard meshing algorithm with an automatic sizing. Fineness was left at 5. No automatic boundary layers have been selected. Physics-based meshing has been activated. So if you hover over it and want to know what this means, you can always hover over the selections right here, and you can see what these actually mean. This hex element core selection has also been activated. Number of processes is again automatic. And for advanced settings, we don't have any small feature suppression right here. So I've already calculated the mesh, and what I added as well are refinements. So what you can do is to click on refinements, and I added boundary layer refinements. And actually you can see if we scroll through the geometry, you can see that for the inlet and outlet there have been boundary layers defined. So you can see the 3 layers right here. These are actually the 3 layers that have been defined right here with a relative thickness of 0.4 and a specific growth rate of 1.5. For the local element size refinement, we have the local element size refinement topological entity set on the right hand side. So we assign it to that and define a maximum edge length of 7 to the power of -4 meters in this case. Great. You can also have a look at the mesh itself. So we can cut through the mesh if you want. So what we can do for this example, we leave it as it is, and we can click on generate mesh clip. Depending on how big the mesh is, this will take a few seconds, and then you can have a look inside of the mesh. So there we go. And as you can see the mesh really inside. It's actually so beautiful to see this and to have this mesh clip filter. That's so cool actually. And I'm always fascinated no matter what mesh I actually generate. What you can actually see is that inside we have these hexahedral elements inside of our core. And that was the setting that we have set in the mesh, which said hex element core. Great. And the mesh clip is always saved. So if you go to mesh clip, so you don't have to worry about generating a new one. And you can really see if you want to make some improvements to the mesh itself. So really awesome feature. Also, we have generated a cell zone, what you can see, and the MRF rotating zone has been assigned to this cell zone, which we actually need. Great. You can also have a look at the meshing log as well as meshing quality parameters. So I didn't run the simulation, so if I wanted to, I could click on this plus. It gives me the duration of the simulation, in this case around 60 to 180 minutes, and it gives me a rough estimate of how many core hours will be consumed for the simulation. I can actually run this simulation. What a lot of people don't know is that you can run multiple simulations. That means I can run one simulation, for example, run one here, run it, and then it will be sent to the server and calculated. At the same time, I can start a second run, third run, fourth run, and so on. What I would generally recommend is to start one simulation, have a look at the outcome, and then see if it really makes sense to run multiple simulations. So as in the cooking show, I have prepared already the post-processing, so which would be my first one. So it's like in the cooking show, hey, I've prepared something. So let us have a look at the outcome. So we have defined the area averages in the result control item, right? So we have a look at the outlet, for example, and at this UI component. And what you can really see and what this is really useful for is you see some fluctuations at the beginning because it's really going to a steady state. And after around 400 to 450 iterations, you can see that the velocity is not changing anymore. So we can consider this velocity for the outlet to be converged. You can do the same for the inlet. In case of a Formula 1 car simulation, for example, there would be the drag. So you could, for example, have a look at the drag, and you would see that the drag also fluctuates and then stays constant at some point. Great. As for post-processing, we can go to this one that I've already prepared, go to post-process results. This will take some time, and then you can cut through your geometry, create slices, isosurfaces, and so on. So I have created a slice right here, or a cutting plane, and you can really see the velocity in meters per second inside of our domain. So really great post-processing features. So feel free to discover them, check out some post-processing capabilities inside of the workbench, or if you want, have a look at them in the documentation. Again, if you have any questions, feel free to reach out to me and I would be happy to help you out. Thank you so much for watching and see you in the next tutorial.